easier to understand. The bright thing here is good and black is bad. And you know you don't want to go this way, but going along this way, you don't know exactly where your corner is. So let's take a look at sort of another patch, another place. And here we are right in the middle of the flower bed. Now, both of our gradients are large. Our lambda, the gradients are large in many different directions, so we have a large L1 and a large L2. We get this nice peak down here, and that's shown as this nice peak here. The idea is that this would have a nice large R value, Harris corner R value, that would find you that says, you know what, if you give me that point, and I'm looking for that point again in another image, any small motion is going to give me a big error change. So that's a good suggestion for where a corner might be. All right, so here is the simple Harris detector algorithm, courtesy 1988, still used today a lot. We're going to talk about different versions of it going forward when we talk about scale and stuff, but for now we're just going to talk about this. And here's the basic algorithm. You first compute Gaussian derivatives at each pixel. Okay, so remember you need this Ix and Iy, and we've talked all about how to do derivatives, where you take the derivative of the Gaussian operator, apply that, and you get back your nice image derivatives. Then you compute that second order moment matrix M, that M matrix that we're talking about, and the recommendation is use a Gaussian window so that you weight the points near the middle more than the points that are further away. And then you compute that R function on that M matrix. Remember, you have a different M matrix for every point in the image, right? Because you take a little window around a point, compute the moment, compute R, move on. So you have one for every point in the image. So you get all these R's, you're looking for high values, you threshold that, and then, and we talked a little bit about this when we were doing the edge detection, you do what's called local non-maximum suppression, right? So I might have I might be a strong R value, but if there's a stronger R value next to me, throw me away and keep him. Sorry about that. But the idea is that you're looking for local areas that have the highest possible R value. And like I said, this was presented originally in this paper in '88. Just to show you some examples, so here we have two pictures. I wish I knew where these pictures came from. These are like so hysterically cheesy. Two pictures of a toy giraffe. You'll notice that a couple of things. First of all, obviously the orientation has changed a lot, but also the head has been rotated, right? So here it's on the side, and here he's facing you, and so things have shifted a bit. The feet are a little different. Of course, the entire object has rotated, and the intensity has changed. So there's been quite a bit of change done to the image. So here we go. We compute our derivatives, we compute our moment matrices, we compute our R functions, we plot them in MATLAB using a interesting pseudo-color color map, and you see this beautiful picture. And that's R everywhere, and the next thing you have to do is threshold that. So here are all the points that R is above some particular threshold. Then we do that trick of the non-maximal suppression, right? So we only keep points that are locally higher value than anybody else. And this is probably pretty hard to see. Megan helped a little bit by putting this line down the middle, so there's this constellation of points on the left and the right. You know, if I look at that, I can't really tell it's a giraffe, but what I can do is I can show you those red points on the actual giraffe itself. There's a giraffe, right? Yeah, it's kind of a weird giraffe. Somebody's fan, it's like a creepy giraffe. It's like always smiling. Anyway, all right, and here you can notice that we've found a bunch of points repeatedly. So for example, on his nose, on the right nostril there's a point right there. Well, guess what? We found the same point right there. So if I wanted to see how the head was changing, right? Points on the ears are there, okay? Points on the back of this spot here are there. Points on the bottom are there. Now, of course, all these points, they're not there. Well, of course not. There's a specular reflection in the left image that's not in the right. That's okay. Harris couldn't possibly know about that. The point is, that we reliably found many of the same points. And if you remember what we were talking about for doing this interest point or key point detector, we need a reliability and a precision. We have to find the same points and find them in the same location on the scene or in the scene. And that was what would make a good feature. I should mention that there have been other attempts at, other pieces of work on finding corners. In fact, she and Tomasi did this nice work on cornerness, and it did something different looking at the lambdas instead of using that R, and found local maximas. And I will tell you, if any of you who use OpenCV, they have something called OpenCV Good Features to Track. It's a function. It finds you points in the image that are good points to track. How does it work? I'm pretty sure that's the Shi and Tomasi version of this. It's still based upon the same moment matrix. It's just a different use of the eigenvalues. And there's reports that maybe it's a slightly better way for things that are undergoing certain kinds of deformations. There was another one, 2005, Brown, Selinsky, and Winder, and I write this one because I've stolen so many of these pictures from Rick Selinsky's book. I feel like I have to put this in there. It again looked at eigenvectors in another slightly different way, and there are other types of corner detectors. That ends our very long lesson on Harris corners. I'm hoping Megan can do some like video magic, so you've actually just seen 3 magnificently edited, cut tight. I hear she's friends with John Williams, so there'll be a score in the background. Anyway, but this notion of variation in gradients is very important in general. It's used for feature detectors, but this notion of gradients varying over a window will be important when we do other issues having to do with motion and stuff like that. But for now, we're just thinking of it as doing point detection. And in the next couple lessons, we're going to take a look at some of the properties of this detector, and then we're going to build some descriptions, some descriptors around those detected points. Are you tired? I'm tired. All I've got to drink is water. I hope you can do better. Welcome back to Computer Vision. Today we're going to continue our exploration of feature detections. Remember last time we started talking about interest points, ways of detecting locations of the image that we can get back to, and we focused on finding corners. And why corners? Well, as we talked about, corners had this nice property that if you put a little operator over an area that was a corner, whether you moved it left or right or however you moved it, you would see a pattern changing. And that was not true if you were over a flat region or over an edge. Over an edge, if you moved in the direction parallel to the edge, you couldn't see any change. And we derived some nice mathematical formulations where we talked about the error as you slid things around. We said how the error was 0 before you do any sliding at all, and that as you move, the error changes a little bit. And what we did was we said, well, can we build a model or can we approximate that error by looking locally at the structure of the image? And then we wrote this out as a expression really just involving what's called the second order moment matrix, that moment matrix being the sum of the squares of the first derivatives. So ix squared, iy squared, or ix times iy. And even though it was a second order moment, there were no second derivatives, right? No I sub xx, because those all went away when we evaluated around u and v being 0, 0. You can go back and review that lecture. And then we talked about how Harris and who, yeah, who knows? No, Harris and Stevens did this thing where you derive an operator based upon that little matrix, based upon its determinant and its trace, and you could use that to find good points. And we showed this horrible giraffe image, and we said, yep, the thing seems to work pretty well finding those points. What we're going to do is now we're going to look at some properties of the Harris detector and actually of one or two other ways of detecting some interest points. Remember, the reason we're doing this is to find points that are going to be our feature points. So let's start with rotation. Okay, if I've got an image, so we have here a little notional corner, and I were to rotate it, how would the Harris operator change? Well, remember that whole thing about the ellipse rotating? Well, the ellipse would rotate, right? But it would be the same ellipse, right? Because the variations in the gradients would be the same over the window. The whole thing would have rotated. So basically, the Harris corner detector is invariant to rotation. That's cool. You don't have to take my word for it. You can take somebody else's word for it. No, you can actually study these things empirically. Right? So the idea is you take some picture, you find some corners, and then you change the picture somehow, right? So maybe you rotate it a little bit, and then you find some corners again, and you measure sort of this repeatability, right? So the number of correspondences that were found versus the possible ones that you should have found. That is, how repeatable was the ability to find the same corners. And as you can see here, as they varied the rotation of the picture all the way up to 180 degrees, you've got pretty good reviews. By the way, imp Harris is improved Harris. But you can see that both Harris and the improved Harris are pretty invariant with respect to rotation. By the way, these plots come from this very nice paper from Cordelia Schmidt and folks there. And in fact, here it is showing you. It's from the International Journal of Computer Vision. I put these sort of basic sources in here just so you can see where some of this stuff comes from. And if you're interested in computer vision, I encourage you to take a look at what these papers actually do to get a sense of how this stuff got derived. What about changes to intensity? Right? I change the intensity somehow. What happens to my corner detection? Well, it turns out that it's mostly invariant to additive and multiplicative intensity changes. So as it says here, look, the moment matrix is just made up of IXs and IYs and the products of them. Well, IX is the derivative in X, IY the derivative of Y. If I add a constant to my image, nothing changes. My derivatives are the same. So it's totally invariant to changes in intensity shift. I just add a value. What if I multiply everything? Well, when you multiply an image, you multiply the gradients, right? Well, when you multiply the gradients, you multiply the R value. And that's what's shown here. Here we have an R function with certain peaks that were above a threshold. And if you were to scale the image by a scalar, you would just grow those peaks, all right? But the shape would be the same. And the only thing you have to worry about is, since you're using some threshold, maybe some points that were above the threshold or below, depending on whether you're going up or down, maybe they would now change which side of the threshold they're on. In practice, intensity variation, multiplication like that is not an issue. What about change to scale? Well, what will be clear is it is not invariant to image scale. So here we have two different curves. Here I have my original curve like this, and here I've just zoomed out and I have a much tighter curve like that. And the little boxes here, those are meant to be the size of the window. And if you take a look at each one of these, all these points will be classified as being edges because essentially there's not much gradient in the directions parallel to the edge. But if I zoom out, this is now a very good corner. And so the problem is that by changing this smooth curve, by zooming out so the curve becomes tighter and tighter and tighter, it goes from being a bunch of edges to being a corner. So in general, the Harris corner finder, corner detector, is not invariant to scale, and guess what? The data prove that. Okay, here's another graph taken from a similar paper, and you can see that it falls off pretty drastically as you get to scale. In fact, even with just a scale factor of 2, so I just zoom in or zoom out by a factor of 2, I've already lost almost 80% of my repeatability. So it's really, really not invariant to scale, and we're going to have to do something about that. So let's just think for a minute. Suppose we wanted scale invariance. How could we do that? So to think about this, let's consider some regions. I'm going to use circles, it's easier to think about, of different sizes around some point. Okay? So here on the left, I've got a curve that is the zoomed in version of the curve on the right, and I've got some circles around this. You know, when I look at the part that's in this circle and the parts in that circle, I say, no, that curve doesn't really look the same. If I make the circle a little bit bigger, no, it doesn't really look the same. How about now? No, not yet. I say, oh, wait. Now, with this bigger size, this piece of curve looks a lot like this piece of curve, all right? So the regions of corresponding sizes will look the same in both images. It's not the same size. I call them corresponding sizes. It spans the same amount of the image. So the problem, of course, is we have to choose the circles independently, because I'm dealing with this image and I got to figure out what scale to do things, and I'm dealing with this image, I got to figure out what scale to do things. And I want it to be the case, the way the red circles are indicating here, that the scale I pick for the left-hand image is this nice big circle, and the scale I pick for the right-hand image is this small circle. So that's what we want to do. We want to be able to do this independently in the images. So how might we do that? Well, here's a solution, okay, and graphically it'll be a little bit easier to see. What we're going to do is we're going to design some function, okay? And it's going to be a function over that circle, and this is a little bit tricky. We're going to call it scale invariant. And what we mean by that is the function doesn't actually care how big the circle is. It just cares about, say, the distribution of the values of the pixels within that circle. So a simple example, not one that we're going to use, but it's